Okay, in this lecture we're going to cover our section 1.4 material on area and arc length in terms of polar coordinates. So the first part of this section will deal with the area of a region bounded by a polar curve. So to set up our problem of interest, let's consider the following. Suppose that we have a polar curve defined by the equation r equals some function of theta for values of theta from alpha to beta. So the question is, what is the area of the region bounded by this polar curve over that theta interval? So let's try to visualize it here. So we would have some curve in the plane defined by a polar equation of the form r equals f of theta. So we saw from our last section that in general, these curves can have sort of unusual shapes. So we have some curve defined by this equation, r equals f of theta, within some range of theta values, say from theta equals alpha. So if we rotate from the positive x-axis by alpha radians up to some other angle measure, theta equals to beta. So what we're interested in is determining the area of this shaded region, which lies between those lines determined by these two angle measures, alpha and beta, and lies inside of that polar curve. When we say inside, we mean closer to the origin than that polar curve. So how can we find the area of such a region? Well, let's think about how to derive a formula for this. So we could start by considering a circle. So a similar problem would be to find the area of some sector of a circle. So let us consider a circle of radius r. So suppose that we have such a circle whose radius is r, and we want to find the area of some sector of this circle, so that is just some part of this circle, determined by an angle measure of theta. So we want the area of just that portion of the circle. So we can say the area of a sector is given by taking the area of the entire circle, which we know would be pi r squared, and then multiplying by a ratio, which would represent the portion of the circle traced out by that angle measure theta. So the ratio that we could look at here, well, theta traces out some portion of our circle, whose total area is pi r squared, and the total circle would be traced out by an angle of 2 pi radians, or 360 degrees. So we're going to take the ratio of theta over 2 pi to represent the portion of that circle, or the sector, which is traced out by that angle theta. So let's see what this gives us. We can see that a factor of pi will cancel in the numerator and denominator. And so we are left with a constant factor of 1/2. And then we have an r squared times theta. So this would be a way to find the area of that sector. So what does that tell us about our problem of interest? Well, if we think about dividing our shaded region into small slivers or small sectors, we see that for this small sector, the area of that sector could be approximated as the area of a sector of a circle whose radius is r, which is given by the value of this function, f of theta. So I could find the area of this small piece shaded in red, which I'll call a differential of the total area of the region that I'm interested in, by using this formula that we found. We would have 1/2 of r squared, but where r is given by our function f of theta. So we would have 1/2 f of theta squared, and then we're multiplying by the value theta, which was the angle measure that we rotated by to trace out this part of our sector. So if we're dividing this sector up into small little pieces, the angle measure that I would be revolving by is what I'm going to call a differential d theta. That is a small interval within that theta variable. So we would multiply by our d theta, and then to get the total area of that region, I would then integrate this expression with respect to theta over the theta interval that defines my region. So starting at theta equals alpha up until theta equals beta. I'm going to add up all of these little slivers, and I'll get the total area of that region of interest. So that brings us to the following theorem for the area of a region bounded by a polar curve. So what we have here is the following. Let's suppose that f is a continuous function which is non-negative on the interval from theta equals alpha to beta, where the difference, beta minus alpha, lies between 0 and 2 pi. So that restriction here means that my polar curve is not like overlapping on itself by making multiple rotations. In that case, the area of the region bounded by the graph of r equals f of theta between the lines determined by theta equals alpha and theta equals beta is given by the following formula. So to get the area, we would integrate the expression that we just found, which was 1/2 of r squared d theta from alpha to beta, or since r is given by a function f of theta, we have 1/2 the integral of f of theta squared with respect to theta over the interval from alpha to beta. So now that we have this formula, let's look at some examples making use of it. So in this first problem, we're asked for the area bounded by the polar curve r equals sine theta plus cosine of theta. So here, using the notation of our theorem, this is the function f of theta, which lies in the sector from theta equals 0 to pi. So using our new formula for area, we would have 1/2 the integral over our theta interval, in this case from 0 to pi, of r, which was given by sine of theta plus cosine of theta, quantity squared, d theta. So let's simplify a little bit. Expanding this, we have 1/2 the integral from 0 to pi of sine squared theta plus 2 sine theta times cosine theta plus cosine squared theta d theta. And we can simplify this a bit further. So we have a 1/2 the integral from 0 to pi of, so looking inside of our integrand, where we have sine squared theta plus cosine squared theta, well, we know that that sums to 1. And then we're still left with the 2 sine of theta times cosine of theta term. So at this stage, we're ready to integrate. And we could start by maybe splitting this integral up into two pieces. It'll make our work a little easier to explain here. So I have first off a 1/2 integral from 0 to pi of 1 d theta, and then plus when I have the constant 1/2 times 2 sine theta cosine theta, that reduces to just sine theta cosine theta d theta from 0 to pi. So here our first integral is pretty easy to evaluate. We would have 1/2 of theta evaluated from 0 to pi, which gives us pi over 2. And then we are adding, well, for this second integral, we're going to have to make use of a substitution. So here we could use the substitution. U is equal to sine of theta, so that du is cosine of theta d theta. And rewriting this integral in terms of u, well, we would need to change our limits of integration from theta values, which were 0 and pi, to values of u. Now u is defined as sine of theta. So for our lower limit of integration, when theta was 0, u is sine of 0, which is 0. And our upper limit of integration, which was theta equals pi, well, u would be sine of pi, which is 0. And then the function that we're integrating in terms of u would be u du. So at this stage, we can immediately see that our second integral is 0 because the interval over which we're integrating consists of a single point. Both the upper and lower limit of integration is the same value. So such a definite integral gives 0, and we're left with a total of pi over 2 for the area of this region being described. Now we could visualize that, of course, if we plot this function using Desmos over the indicated interval, we can see what exactly this region of interest looks like. So let's look at another one. In this next problem, we're asked to find the area of one petal of the rose curve defined by r equals 4 sine of 2 theta. So here, as a reference for this problem, I've given the plot of that rose curve, a little review of rose curves in general. Here we see that r is 4 times sine of 2 theta. So this constant 4 out in front gives us the length of a petal. So the total length that we're moving outward here would be r equals 4, which we can see along that polar axis. So we've got 4 units. And the fact that we have a sine function means that that initial petal opens not along the positive x-axis, but at some angle above that positive x-axis. Now the argument of that sine function was 2 theta. So if this constant for the multiple of theta, in this case k, is equal to 2, is even, then we see that we have twice as many petals, hence 4 petals. So that k equals 2 is why we have a 4-petaled rose here. So what we're trying to do is find the area of one of these petals. So let me just shade in this first one, and we want the area of it. So we have a formula for the area bounded by a polar curve over a given interval, but the problem here is to determine, well, what is the theta interval that defines that first petal? Now in this particular example, we can see, well, it's not too difficult to determine that this first petal is traced out in the first quadrant, which would be determined by the theta interval, theta equals 0, or the positive x-axis, up to theta equals pi over 2, or the positive y-axis. But to show how we might find that algebraically, which will be useful in some of our later problems, well, we can see that first petal is traced out from the origin back to the origin. That is from r equals 0 to r equals 0. So to determine that theta interval of interest, we could take r, which is defined as 4 sine of 2 theta, and set it equal to 0. So dividing by 4, that means that sine of 2 theta is 0. Now the only way that sine of an angle is 0 is if that angle, in this case 2 theta, is equal to some multiple of pi. So 0, positive pi, 2 pi, 3 pi, so on. So solving for theta, we could divide by 2, and we would have 0, pi over 2, pi, 3 pi over 2, and so on. So this first petal is traced out on that initial theta interval from 0 to pi over 2, which we can also see from the indicated figure. So in order to find the area of that first petal, we make use of our new formula. So the area bounded by a polar curve is given by 1/2 of the integral, in this case as theta ranges from 0 to pi over 2. We trace out that first petal. And the function that we're integrating is r squared. Now here r was 4 sine of 2 theta. So we're squaring that quantity and then integrating with respect to theta. So let's see what we'll have here. So when I square this term, I'll start by taking my 4 squared, which is a 16, and then factoring that constant out in front of the integral and grouping it with the constant 1/2, I have 16 over 2, or 8, times the integral from 0 to pi over 2 of sine squared of 2 theta d theta. Now recall, in order to integrate even powers of sine or cosine, we have to make use of a half-angle identity. And the one that we would use for sine squared is that sine squared is the same as 1 minus cosine of twice the angle that we were working with. Now in this example, we already had a 2 theta, so doubling that angle gives us a 4 theta all over 2 d theta. So as a reference, the trig identity, which I'm making use of here, a little scratch work to the side, is that sine squared of an angle is the same as 1 minus cosine of twice that angle over 2. So simplifying a bit further, I see that I have this factor of 1/2 in my integrand, which I can bring out in front of the integral, and multiplying by the constant 8 that we had, we now have 4 times the integral from 0 to pi over 2 of 1 minus cosine of 4 theta d theta. So at this stage, we're ready to find our antiderivative. So we have the constant 4 out in front. The antiderivative of 1 with respect to theta is 1 theta. And then minus the antiderivative of cosine of 4 theta, we would have a 1/4 sine of 4 theta. and we're evaluating this on the interval from 0 to pi over 2. So substituting in pi over 2, we have 4 times pi over 2 minus 1/4 of sine of 4 times pi over 2 would give us sine of 2 pi, which is 0. And then we subtract the value that we get when we substitute in 0 for theta. So we would have 0 minus 1/4 sine of 0, which is still 0. So we're left with 4 times pi over 2, which gives us 2 pi for the area of 1 petal of that rose. So let's consider another problem. It's fairly similar. This next one, we want the area enclosed by the cardioid defined by r equals 1 minus sine of theta, which is shown here in the indicated figure. So we want to find the area enclosed by that cardioid, so we need to think about the interval over which we're going to integrate. Now we had seen in the first part of, or in our last section where we were sketching polar curves, that this full cardioid is traced out over the theta interval from 0 to 2 pi to get a full trace of this cardioid. So we're going to integrate from 0 to 2 pi here. So let's take a look at this. Our area is found by integrating half of r squared over our theta interval, which was from 0 to 2 pi to trace out the full cardioid. Now we were taking r squared, which is 1 minus sine of theta, quantity squared, d theta. So in order to integrate this, let's expand. We have a 1/2 integral from 0 to 2 pi of, expanding 1 minus sine squared, we have 1 minus 2 sine theta plus sine squared theta d theta. So I have a 1/2, the integral from 0 to 2 pi of 1 minus 2 sine of theta. And again, where we have that sine squared theta, we're going to make use of the trig identity. Sine squared of theta is 1 minus cosine of twice that angle, so 2 theta, all over 2, d theta. So simplifying maybe a bit further, I have 1/2 the integral from 0 to 2 pi of, well, let's group like terms together. So grouping my constants, I have a 1 and then plus my 1/2 gives me 3/2. Then I have my minus 2 sine of theta, and then I'm still subtracting a cosine of 2 theta over 2, or 1/2 cosine of 2 theta. So at this stage, I'm ready to find my antiderivative. I still have a constant of 1/2 out in front, and my antiderivative will be 3/2 theta. The antiderivative of negative 2 sine theta would be a positive 2 cosine theta. And the antiderivative of the negative 1/2 cosine of 2 theta is negative 1/4 sine of 2 theta, which we're then evaluating from 0 to 2 pi. So we have our constant 1/2 out in front, and when we evaluate at theta equals 2 pi, we will have 3 pi plus 2 times cosine of 2 pi, which is 1, So 2 times 1 gives us 2. And then minus 1/4 times sine of 4 pi, which is 0. And then we subtract what we get when we substitute in theta equals 0. So 3/2 times 0 is 0. Then we have a 2 times cosine of 0, which would be 2. Minus 1/4 times sine of 0, which would be 0. So we're left with the following. Now here we can see, of course, our positive 2 and negative 2 will cancel. And we're left with 1/2 times 3 pi, or 3 pi over 2. All right. So let's look at some other problems related to the area enclosed by a polar curve. So a similar problem of interest is something like you had seen in the beginning of your Calculus 2 course. How do we determine the area bounded by two curves in the plane? Well, if we have two polar curves, we might be interested in finding the area of the region between those two polar curves. Now, in order to do that, to determine that area of a region between two polar curves, we will often need to find the points of intersection of those curves to determine the region over which we're going to integrate, and also to determine which function defines the outer or the inner curve. So much like you did in the beginning of Calculus 2 to find the area between two polar curves, you can integrate the outer curve minus the inner curve. So that is, you're finding the area inside of the outer curve and then subtracting the area inside of that inner curve, and that difference will give you the area of the region between them. So let's see how this works. We'll look at a couple of examples here. So in this first one, we're asked to find the area of the region that lies inside the circle. R equals 4 cosine theta, which is the circle shown here. And outside of the circle, R equals 2, which is the circle centered at the origin of constant radius 2. So the area that we're interested in is inside of this red circle, but outside of the blue one. So this sort of crescent shape shown here. Now, in order to determine that area, we're going to integrate the difference of those two functions, that is outer function minus the inner function, over the theta interval, which defines our region. So that's what we need to find. What is our theta interval describing that region? So we can see that it ranges from theta equals some angle measure given here where those two curves intersect, up to theta equals a similar angle measure, just finding the other point of intersection of those two curves. So we need to find where these guys intersect, and to do that, we're going to set these values of R equal to one another. So that is R, which was 4 cosine theta, will be set equal to R, which was 2. So we find then that cosine of theta is equal to 1/2. And so theta would be equal to pi over 3 radians. So we see this first angle measure corresponds to theta equals pi over 3. And then, of course, since that region is symmetric, this other angle measure would be negative pi over 3. That is just a clockwise rotation by the same angle measure. Okay. So we can set up our area of this region as half the integral from negative pi over 3 to positive pi over 3 of the outer function squared. Now our outer function was 4 cosine of theta, so we're squaring that, minus our inner function, which was the circle r equals 2 squared, and we're integrating with respect to theta. Now, in order to make our work a little bit easier, we can make use of the symmetry of this region. So in particular, if I were to find the area of the upper half of this crescent shape, that is from theta equals 0 up to pi over 3, I could then double that value to get the area that I'm interested in. So by using symmetry of this region, I could take twice of the area of that half of this crescent, which would be given by half the integral from 0 to pi over 3 of my function, which if we square this, we have a 16 cosine squared theta minus 2 squared, or 4, d theta. So we can see here, well, our 2 times the factor of 1/2 from the formula will cancel, and I'm left with the integral from 0 to pi over 3 of 16 cosine squared theta minus 4 d theta. Now, in order to integrate cosine squared, again, I have to make use of a trig identity. So let me write it out here. The identity is that cosine squared of theta is 1 plus cosine of twice the angle, so 2 theta, all over 2. So when I have 16 times that cosine squared, well, multiplying this expression by 16, that's 16, and then with the factor of 1/2 that I get from my identity, reduces to 8. So we have the integral from 0 to pi over 3 of 8 times 1 plus cosine of 2 theta minus 4 d theta. So grouping some like terms together, I have a constant 8 minus 4, which leaves us with 4, and then plus the 8 times cosine of 2 theta d theta. So finding our antiderivative, we would have 4 theta plus 8, so taking the antiderivative here, antiderivative of 8 cosine 2 theta, when we pick up a factor of 1/2 is 4 sine of 2 theta, which we're then evaluating from 0 to pi over 3. So plugging in pi over 3 for theta, we have 4 pi over 3 plus 4 times sine of 2 pi over 3. So let's see, for sine of 2 pi over 3, we would have root 3 over 2. So simplifying just a little bit further, we have 4 pi over 3 plus 4 times root 3 over 2 is 2 times root 3. So this would be the area of that region of interest. Okay. So let's look at another one where we're finding the area of a region between two polar curves. So in this next example, we want the area of the region inside the circle r equals 3 cosine of theta, which in our figure is shown here. It's the circle, and which lies outside of the cardioid. R equals 1 plus cosine of theta. So that cardioid is shown here. So the region of interest is inside the cardioid, but inside the circle, but outside the cardioid. So the area of this crescent-shaped region shown here. Now, in order to determine the theta interval over which we're going to integrate, we need to find the points of intersection for these two curves, which we can do by setting them equal to one another. So that is 3 cosine of theta will be set equal to 1 plus cosine of theta. So moving all of the cosine theta terms to the left-hand side, we have 2 cosine of theta is 1. So cosine theta is 1/2. And again, we see that theta would be equal to positive pi over 3 or negative pi over 3. Same theta values that we had in the previous example. So again, making use of the symmetry of this region, rather than integrate from negative pi over 3 to positive pi over 3, I could integrate from 0, that is theta equals 0, up to theta equals pi over 3. And then that would give me the area for the top half of my region, and I could then double it. So to set up our formula for area, we're going to take twice the area of that top half of this region, which is half the integral from 0 to pi over 3 of our outer function squared. So the outer function was 3 cosine of theta squared minus the inner function, which was 1 plus cosine of theta quantity squared, integrating with respect to theta. So as with that previous example, we can see that our factor of 2 and 1/2 cancel one another. And so we have the integral from 0 to pi over 3 of, well, expanding, we have 3 cosine theta squared gives us 9 cosine squared theta, minus the quantity, expanding 1 plus cosine of theta squared, we have 1 plus 2 cosine of theta plus cosine squared of theta, which we're then integrating with respect to theta. So simplifying just a bit, we have the integral from 0 to pi over 3, and this 9 cosine squared theta, and then minus our cosine squared theta, we can group together as 8 cosine squared theta, minus, we have a 1 and minus 2 cosine of theta d theta. So now, again, to integrate this cosine squared theta term, we're going to make use of the same trig identity we had written above, namely that cosine and squared of theta is the same as half of 1 plus cosine of 2 theta. Now, since we're multiplying by an 8 out in front of that cosine squared theta, this reduces to a 4 times 1 plus cosine 2 theta. And then I've got my minus 1 minus 2 cosine of theta. So simplifying just a bit more before we proceed, we have the integral from 0 to pi over 3. My constant term would be 4 minus 1, which leaves me with 3, plus I still have a 4 times the cosine of 2 theta minus 2 cosine theta d theta. So finally, I'm ready to find my antiderivative. So we have for this function, 3 theta, plus the antiderivative of 4 cosine of 2 theta would be 2 sine of 2 theta. And then minus the antiderivative of 2 cosine theta would be 2 sine of theta, which we're then evaluating from 0 to pi over 3. Okay. So let's see what we get. Substituting in theta equals pi over 3, we have pi plus 2 times sine of 2 pi over 3 gives us a root 3 over 2. And then we have a minus 2 times sine of pi over 3, which is also root 3 over 2. And then we subtract the value that we get when we substitute in 0. So plugging in 0 for theta, we're left with 0. And we can see here that the 2 times root 3 over 2 minus 2 times root 3 over 2 will cancel one another. And so we're left with pi for the area of that shaded region. Okay. Now, in the last part of this section, we'll talk about how to find the arc length of a polar curve. So let's say that we have in the plane some curve defined by the polar equation r equals f of theta, and we want the total length along that curve from one end to the other. So how can we find this? Well, the following theorem gives us a formula for arc length of a polar curve. So here's what it says. If we have f, which is a function whose derivative is continuous on the interval from theta equals alpha to theta equals beta, then the length of the graph of this polar equation, r equals f of theta, from theta equals alpha to beta is given by the integral over that theta interval from alpha to beta of the square root of r squared plus the derivative of r squared with respect to theta. Or since r was given by a function, we could also write this as the square root of that function squared plus the derivative of that function squared. So let's look at an example of this. In this last problem, we are asked to find the length of the polar curve r equals theta squared on the interval from theta equals 0 to pi over 2. So using our new formula for the arc length of a polar curve, we have that arc length L is given by the integral over our theta interval, here from 0 to pi over 2, of the square root of r, which was theta squared, squared, plus the derivative of r, which would be 2 theta, quantity squared, integrating with respect to theta. So in order to integrate this function, we need to simplify the integrand a little bit. So under the radical, if I square each term, well, theta squared squared gives me theta to the 4th, and then plus my 2 theta squared gives me 4 theta squared d theta. Now from under that radical, or from the expression under the radical, I can factor out a theta squared from each term, which leaves me with theta squared plus 4 d theta. And then taking the square root of that, I have the integral from 0 to pi over 2. Now the square root of theta squared is just theta. And then I'm left with the square root of theta squared plus 4 d theta. So at this stage, I can find my antiderivative of this function by using a substitution. So I'm going to make the substitution u is equal to theta squared plus 4, the inner function in my composite function, so that du is given by 2 theta d theta. So changing my integral for arc length, which was 0 to pi over 2 theta square root of theta squared plus 4 d theta, to an integral in terms of u, well, let's see what we have. So first we need to convert our limits of integration from theta values to u values. So let's see what we have here. Our lower limit of integration was theta equals 0. Now if theta is 0, we can see that u would be 4. So our new lower limit of integration is 4. And our upper limit of integration was theta equals pi over 2. So substituting that into our expression for u, the new upper limit would be pi over 2 squared, or pi squared over 4, plus 4. And the function that we're integrating is now the square root of u, and then this factor theta times d theta. Well, solving for theta times d theta, we would have du divided by 2. So I pick up a du with a factor of 1/2, which I can bring out in front of the integral. So now I have my constant factor of 1/2 times the antiderivative of root u, which is 2/3 u to the 3/2 power. And then evaluating from 4 to pi squared over 4 plus 4. So simplifying the constants, I have half of 2/3, which would be 1/3. And then I'm multiplying by u, which, evaluating at my upper limit, I have pi squared over 4 plus 4 to the 3/2 power, minus 4 to the 3/2 power, which is the same as 2 cubed, or 8. So this expression would be the value for the arc length of the indicated polar curve over that interval from 0 to pi over